Have you ever really stopped to think about how we give directions? It's something we do all the time, but hidden inside that simple act is the key to one of the most powerful tools in all of science, the vector. Today, we're going to deconstruct that very idea. We're going to build it all the way back up, from a simple arrow on a map to a full-blown description of motion in 3D space. All right, let's dive in.
So let's just start with a super simple question. If a friend asks for directions, what do you tell them? You might just point and say, oh, it's about 50 kilometers that way. I mean, it's intuitive, sure, but it's also incredibly vague. That way isn't exactly precise, is it? And that right there, that's the exact problem vectors were invented to solve.
Now check out the contrast here. Instead of saying 50 kilometers that way, what if you said, go 40 kilometers east, then 30 kilometers north? See, suddenly it's crystal clear. There's zero ambiguity. This second method, breaking a journey down into its basic parts, its east-west part and its north-south part, that is the very heart of what we call vector components.
So here's our roadmap. We'll start by making that better way to navigate a little more official. Then we'll get into the real meat of it, breaking vectors down. After that, we'll see how to figure out a vector's true length and angle, how to work backward from those, and then, finally, we'll take our new toolkit and jump into 3 dimensions.
Okay, let's jump right into Section 1, finding a better way to navigate. This is where we stop vaguely pointing and start using the precision of coordinates. We're about to turn a simple arrow into a seriously powerful tool for analysis.
And a tool that makes all of this possible is the Cartesian coordinate system. You've definitely seen this before. It's just the good old XY plane. Think of it as the ultimate piece of grid paper. The horizontal x-axis, that can be our east-west direction, and the vertical y-axis, that's our north-south. Now, any journey, any movement at all, can be drawn as a clean arrow on this map.
All right, let's move on and see how this all leads to our main event, breaking vectors down. It's time to look under the hood of that arrow and see what it's really made of.
Okay, this is the crucial idea. Any vector, and I mean any vector, no matter which crazy direction it's pointing, can be perfectly described by its components. Picture this. You shine a giant flashlight from directly above the vector. The shadow it casts on the x-axis, that's its x component. Now shine a light from the side. The shadow on the y-axis is its y component. These two shadows are its fundamental building blocks.
And this is really the core idea, laid out perfectly right here. The total trip, vector A, is just what you get when you add its east-west part, a sub x, to its north-south part, a sub y. It's exactly like our 40 kilometers east plus 30 kilometers north example. The math is just a clean, simple way of saying the exact same thing.
Now, to write this stuff down like a physicist, we need a special language. So meet the unit vectors, e hat and j hat, or as we say, I hat and j hat. They're incredibly simple, but so important. I hat just means one step in the positive x direction, and j hat means one step in the positive y direction. They're pure direction. They're basically just little signposts.
And now we can put it all together. The complete component form of a vector tells us everything we need to know. It says, here's how far to go in the x direction, that's the number a sub x, and here's how far to go in the y direction, that's the number a sub y. It's a complete, perfect, unambiguous set of instructions.
Let's make this real with a mouse pointer. Say it starts at one point on your screen and ends at another. To find the vector for that movement, we just subtract the starting coordinates from the ending ones. The x component is just the final x minus the initial x, which gives us negative 4.0 centimeters. The y component is the final y minus the initial y, which is positive 2.9. So our final vector tells us the pointer moved 4 centimeters to the left and 2.9 centimeters up. Simple as that.
Okay, so we're pros at breaking vectors down. But what if we want to know the actual direct straight line distance the mouse pointer traveled? Well, that brings us to Section 3, how to get the vector's overall length, its magnitude, and its direction from those components.
Take a look at the components and the vector itself. If you draw them out, what shape do you see? It's a right triangle. The x and y components are the two short sides, and the vector itself is the long side, the hypotenuse. So to find its length, what we call its magnitude, we can just pull out the good old Pythagorean theorem.
Now, for direction, we need a standard, a rule everyone agrees on. Physicists define the direction angle theta as the angle you get when you start at the positive x-axis and sweep counterclockwise. This way, we're all measuring from the same starting line and in the same direction. So an angle of 144 degrees means the exact same thing to every single person. No confusion. So let's go back to our mouse pointer. When we plug its components into our formulas, we find its magnitude, the straight line distance it moved, is 4.9 centimeters, and its direction angle is 144.1 degrees. And there you have it. We now have a complete, precise description of its movement.
Okay, let's flip this whole problem on its head in Section 4. What if you already know the magnitude and direction? Let's say a plane flies 200 kilometers to the southeast. How do you find the components of that journey?
For this, we just need a little bit of basic trigonometry. And these two simple formulas are all you need. The x component is just the magnitude times the cosine of the angle, and the y component is the magnitude times the sine of the angle. This lets us translate any kind of directional instruction into our standard x and y language.
And this slide right here shows you just how powerful this is. Look at this crazy journey Trooper the dog takes. He goes southeast, then due north, then 30 degrees west of north. It's all over the place, right? These are all different ways of describing a direction. But by using our simple trig formulas, we can convert every single leg of his trip into a nice, clean, standardized list of x and y components. This makes a really complicated problem suddenly much, much easier to handle.
So far, we've been living in a flat 2D world. But we live in a 3D world. So for our final section, let's expand our toolkit. Let's take it into three-dimensional space.
And you know what the beautiful part is? It's incredibly easy. To go from 2D to 3D, all we do is add one more axis, the z-axis, which usually stands for the vertical direction, up and down. And with that new axis comes one more unit vector, k-hat, or k-sharp, which just points in the positive up direction. Now what's so cool is how our formulas just extend. A 3D vector is just the sum of its x, y, and z components. And the magnitude? You guessed it. We just add the z component squared under the square root sign. The logic that we built up so carefully in 2D scales up perfectly to 3D. It's so elegant.
And here's a great little insight into why that formula works. As the source material puts it, this expression for the vector magnitude comes from applying the Pythagorean theorem twice. Think about it. First, you find the length of the vector's shadow on the xy floor. Then you use that length and the vertical z component as the two sides of a new right triangle to find the final 3D length. It's really clever.
And to see it all come together, let's track a drone. It moves from one point in space to another, changing its position left to right, forward and back, and up and down. By finding the three components of its journey and plugging them into our 3D magnitude formula, we get a single clear answer. Its total displacement was 2.11 kilometers.
So there we have it. We went from a vague wave of the hand all the way to a precise mathematical language that describes movement in 3D space. We've built this amazing toolkit. So the final question is, what are you going to do with it? The next time you see some complex motion, a ball flying through the air, a satellite orbiting the Earth, start thinking about its components. How can you start to break that motion down into its fundamental parts?